So we introduced the concept of electric field, and we said just like gravitational field, there was two ways to calculate the electric field. If you knew the planetary charge that was sending out the electric field, you could go kq over r squared. If you knew not what the planet was, but you could feel the electric force acting on a test charge in that location, like a satellite in orbit, you could figure out the electric field, newtons per coulomb. The only issue we said here was stuff can fall up. And so we had to define which way the direction was for electric field. And we said this, we're going to define the direction as which way a positive sitting at that location would want to move if it could. Let's do something. So we said, but let's talk about it in terms of a positive. Okay? So we looked at these two here. We said, test charge, if a negative test charge feels a force to the south, the electric field on a positive, the direction would be to the north. We said, what would the electric field be right there? Well, this is positive. A positive charge would feel a force to the right. Part C says, draw the electric field around a positive charge. So we're going to do what are called electric field diagrams. I won't ask you to draw one, but I'll probably ask you to interpret one or two. What is an electric field diagram? To visualize this, we draw lines. So if you would be so kind as to draw a little line, let's say right here, right here, right here, and right there. Found it okay? Okay. What direction will the arrows that I put on these electric field lines point? Well, it's which way a positive would want to move if it could. So sitting right here, which way would a positive want to move if it could? I'll put a little arrow right there. Which way would a positive want to move if it could? How about on the bottom? How about here? That would be a picture of the electric field lines coming from a positive charge. Let's compare that with the electric field lines coming from a negative charge. So next page. How many lines did I draw on this negative charge? How many did I draw on the positive? I'm not saying the positive is 4 coulombs, and I'm not saying the negative is 8 coulombs. I am saying the negative is twice as big a charge. So the more lines compared to another charge, the bigger the charge, and we usually do it as ratios. And which way would the electric field lines point here? Here they would point inward. And I would be able to say, if I told you the positive charge was 4 microcoulombs, this is negative 8 microcoulombs. If I told you the positive charge was 10 microcoulombs, this is negative 20 microcoulombs because of the number of lines. I have a little sim here. It's called Electric Field of Dreams. It's this one here. Lovely sim. It's running in old Java, so it has to do a bit of a browser conversion. Give it a couple seconds to think about things, and then it will initialize. Hope it will initialize. There we go. So I'm going to put a charge. Is that charge negative or positive, and how can you tell? Why? Because the electric field lines are pointing towards it. So which way would a positive charge want to move? Towards it. So it must be negative. Add a second charge. This is what's going on. These two, what's that second charge? Also negative. So like charges, okay. They're going to constantly exert a force in this little trapped area. I'm going to go to properties. And those of you at the front can see I'm going to make the charge from negative 1 coulomb to positive 1 coulomb. Same mass as before. I'm going to add it in. Now we have 3 charges moving around. They're doing all sorts of stuff. It's really, really interesting. This charge right here, negative or positive, and how can you tell? Why? Okay, what about this one? What about this one? Is that another one? Let's add another one. Let's add another one. Let's add another one. This is what's going on at the molecular or subatomic level all the time. This interaction, repulsion, and attraction of charge. This charge right here, negative or positive? How do you know? Okay. What about this charge right here? Okay. What about this charge right here? Okay. We had to define what direction the electric field would be because stuff can fall up. So our definition is which way would a positive feel a force? Which way would a positive want to move if it could? Back to zero. So what's the direction of the electric field? We ask, which way would a positive charge at that location want to move if it could? The short version is electric field lines always point from positive to negative. And I've seen some textbooks just teach that. The problem is sometimes you'll only have one charge in the picture, and I found kids got confused because, well, I see the negative, but where's the positive? So it's which way would a positive want to move if it could from positive to negative if there's two charges. I am going to ask you to find the overlapping electric field created by two charges. I guarantee, like in example 6. It says, find the electric field, magnitude and direction at the field point right there. We're going to use something that we call the principle of superposition, which is a fancy phrase for saying there's no way to find the electric field from two charges. You find them one at a time, and then you add them vectorially. That's the principle of superposition. So, problem. This is a common error, and I need to lovingly beat this out of you. Donald, what does example 6 want me to find?
Electric field.
The number of times I see kids go, electric field starts with F, so they must want me to find this. And the problem is, you can find that. Did they give me Q1? Did they give me Q2? Did they give me R? And I have to give you 0 because that's not what I asked for. I mean, you may have done it right. And so the word you really want to trigger on is field, which is not a force. It's not measured in newtons. Do we have more than one charge in this picture, Donald?
Yes.
Do yourself a favor. Let's call that one Q1. Let's call that one Q2. Label the charges. It's much easier. What I'm going to do, Donald, is I'm going to find the electric field from charge 1. I'll call that E1. Magnitude and direction. Did they give me a distance in meters? Which electric field equation am I going to use here?
KQ over R.
K, Q1 over, and yeah, we pronounced that R squared.
Yeah.
R2. It's not battleship, it's math. R2. B3. No, it's B cubed. Donald, what's K?
9 times 10 to the 9.
Q1 is 1, and then microcoulomb is 10 to the negative 6. That's why I said it's worth memorizing. Why am I always giving you microcoulombs? I think I told you 1 coulomb is massive. It would fry you. So I want to try and give reasonable values. Over 1 squared. I mean, there's lots of ones here, but there's powers and exponents. If you want to use a calculator, you can. Think you're going to get 9,000, but double check me. $9,000? Units, electric field. Newtons per coulomb. Direction. So what we're doing now is we are imagining that this charge here doesn't exist at all. Which way would a positive sitting right there want to move if it could because of that charge Q1?
All right.
Can I say east?
Yes, if you want to say east, go ahead. Now we're going to find the electric field from the second charge. And again, Hannah, did they give me a distance? Sort of. Definitely I see meters, so it's going to be KQ2 over R2 squared. And you know what, Donald? I probably should have written R1 right there. Hannah, my angel, you got to be a little bit careful. Look up. What's this distance? Please don't say 4. What is it? Yes, okay? So don't just blindly... Would I have an answer with the 4 there? Yes, I would if it was multiple choice, because that's a sloppy mistake. What was K again, Hannah? Good. And it looks like Q2 is also 1 microcoulomb over 3. Don't forget the squared. Right, Allie? Right. I think this one ends up being 1,000. Yes? I can do this one in my head as well. Units, Hannah? Good. Direction. So now, Hannah, in your mind, imagine this one gone. Which way would a little positive sitting right there want to move if it could because of that guy? Left. Any thoughts on how I would add 9,000 right and 1,000 left? You know what? This is winner minus loser. It's really what we were doing with that. So they'll either be in the same direction, then Alexis, add them up. If they're in opposite directions, bigger minus smaller, or to put it in terms we've already, winner minus loser. It's not a force, but we can do that. So it's going to be 9,000, take away 1,000, 8,000 newtons per coulomb. Direction.
Right.
Right? Right. I can ask you to find the electric field between two charges, or I could give you a point over here. I'd have to give you some more distances, or I could give you a point way over here, or I could give you an electric field with two charges that were at angles. This time we wouldn't say components. We would say you're going to add the tip to tail. Example 7 says, draw approximately the resultant electric field at the indicated field points. Assume both charges are positive 1 microcoulomb, like the example we just did. Okay. I'm going to do these weird ones last. In fact, I'm going to start dead center. Imagine the right-hand charge. Oh, you know what? Let's call it Q1 and Q2. Imagine Q2 is gone. Which way would a tiny positive charge sitting right there want to move if it could because of Q1? So there would be a little electric field pointing to the right. Which way would a charge want to move if it could because of charge Q2? Would the electric field be bigger, smaller, or the same size? I think same size. In fact, you know what the net electric field is right there? You could leave it blank, and I would have to say you're correct. What about what about this one here? I'll change colors. Which way would a positive want to move because of Q1? So there would be an electric field pointing to the right. Which way would the electric field from Q2 be pointing? To the left, but why smaller? Further away. And so I would argue the net electric field, what that means is a positive sitting right there would start to accelerate to the right. Right here, it would not feel any force because there's no net electric field. It would just keep going in a straight line at steady speed. What about right here? Which way do you think the electric field is? For the same argument, we can say, okay, this would push to the left. Q1 would apply a force, an electric field to the right. The net electric field would be, oh, change colors, Mr. Dewick. That way. What about up here? Let's see. Which way would this be exerting an electric field? I think up and right. Which way would Q2 be exerting an electric field? How would I combine those two? You said it. What? So because I can, I'm going to go like this. What's the net electric field direction actually? Vertical. Yeah. What about right here? There would be some electric field pushing vertical, and there would be some electric field kind of pushing sideways, but not very big. Again, if I add it tip to tail, I get nearly, but not quite vertical, a tiny bit of a push to the left, a tiny bit of an electric field to the left. So example 8 says, draw the electric field pattern for like charges. This is a good example of an electric field diagram that we're going to do. First of all, we would say this. Anything that left right here would get repelled. The electric field would go that way. A positive would travel in that path. A positive charge would travel in that path. Also going down, a positive would go like that, a positive would go like that. Why did I do 2 lines on each? What's the first word of part A? Equal. If they're equal charges, they have to have the same number of lines. So I could also say probably something like that and something like that. Not very even, Mr. Duke. Probably something like that and something like that. Something like this. Something like this. Something like that. Something like that. Well, there's what I was trying to go for. There's one done with fancy schmancy computer graphics. Is that kind of what we have?
Close.
Yeah. What about for equal and opposite charges? Well, first of all, there would be a line going yump like that. Which way will I put the arrow on that line? Pointing to the left or pointing to the right? Because which way would a positive want to move if it could? I'm going to change colors so it doesn't overlap, because they're going to overlap a bit, so I'll do it in red. There would be a line that would leave here and yump end up there. There would be a line that would leave here and end up there. There might be something like this. Yum. Usually right around now, someone says it's starting to look like a frog's head. Yum.
Does.
Okay. There would be a line that would exit the page over here and come back on the page over here. It would just go off, right?
Yeah.
There would be one that would go off the page here and come back on here. And these would be the paths that if you had a really tiny no mass positive charge, that would actually follow that path. And I could keep adding more if I wanted to. But again, if I spoil the punchline, it's supposed to look kind of like that. Okay? So once you've drawn your electric field lines, just for practice, I won't ask you to draw electric field lines on a quiz or a test, but here's what I will do. If you look up, I'll give you a picture like that, and I'll say, which one is positive, which one is negative? And how do you know? Okay? Or, I'll give you a picture like this, and I'll say which one's positive, which one's negative, and how do you know? That would be a nice multiple choice question. Positive, 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 negative, 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 positive. In fact, I just told you the 4 answers I'd probably have you pick from. Problem solved. Okay? Yeah?
Would it lead straight out away from the electron?
From the positive?
For the positive, it leads straight away.
Towards the negative? Yeah.
No, straight away. How does it grab?
Oh, when it goes straight away from it? Because it does.
Okay.
You're talking this one here.
Yeah.
Okay, it doesn't actually wrap around. What it would be saying is if you put a positive there, it would eventually end up out at infinity on the left. If you put a positive there, it would eventually end up in infinity on the right, as long as they were exactly straight. Max? Here? Yes, but that's what those arrows are showing, right? It's just that the direction of the electric field we defined as which way would a positive sitting there want to move that could. The concept of electric field and field lines originated with Michael Faraday, and I got to go on a bit of a nerd rant about probably my favorite scientist, Michael Faraday. Michael Faraday had a really fascinating background. He was born into a very poor family, but he was brilliant. He actually got a job with an uncle as a bookbinder back in what would have been about 1805. He would have been in his teens. Back then, books were sewed by hand, and it was a pretty good job. At that time, only wealthy people could go to university. Poor people, no chance. And so one of the things that was done, there was something called the Christmas lectures, which are still going on. The Royal Academy of Sciences would do public lectures for the lay public, for poor people. And kind of what I did with you yesterday with the Van de Graaff, like they would put on a science-y show. Not with electricity necessarily, but with the latest science of the day. And at that time, one of the scientists was a guy named Sir Humphrey Davy. He did a presentation. Faraday was in the audience, and Faraday took meticulous notes, bound it in a book, and sent it to Davies. And Davies recognized, hey, this kid's got something. So he hired Michael Faraday as a lab assistant. This was Michael Faraday's entrance into science, and Faraday was passionate about science. We say that Faraday may have been the greatest experimentalist of all time. And what do we mean by that? If you needed to come up with an experiment that would eliminate every variable but the one that you were interested in, he was the king of coming up with something that did that. He was brilliant. He also was horrendously jobbed by Sir Humphrey Davy. For about 20 years, Sir Humphrey Davy took credit for all of Faraday's discoveries, and out of loyalty, Faraday never said anything. Faraday is the father of electricity and magnetism. He invented the electric motor and the electric generator, which kind of power everything. He was very lousy at math, but he was very good at English explanations and diagrams, hence the electric field lines, because you can do that mathematically. He didn't know how to do it mathematically. He phrased some of his most famous discoveries as English paragraphs, not as mathematical lines. And when he died, he was so famous that Queen Victoria offered him burial in Westminster Abbey near Isaac Newton. He turned it down. A very religious man, very humble, not for me. I always liked Michael Faraday. When he had tried to show to Parliament the usefulness of electricity and Parliament just didn't get it, Parliament said to him, "So what use is this?" And Faraday proved himself a pretty smart politician. "I don't know, but you'll be able to tax it someday." "Oh, okay, we'll fund it." Good answer. So, the idea of an electric field originated with my man, Michael Faraday, but he used a different way of representing the field. Rather than an equation, he used lines of force, which showed the direction in which a positive test charge would tend to move if placed anywhere in the field. So here are some pictures. I think I have a sim for that too. Yeah, charges and fields.
How do you know that happened?
Experiments. He just did experiment after experiment and had many, many, many aha moments. Okay? So here is your electric field, or if I just turn on direction only, there you go. Okay? The darkness and lightness is attempting to show the strength of the electric field, but there's an electric field. Okay? What if I put another charge in? They all start to interact. What if I put another charge in? All the fields start to interact. What if I put another charge? What if I put another charge? What if I put another? They all start to interact. You're going to find that out the hard way when I give you the most addictive bonus video game ever. So what's our summary? The electric field can be found. Using the definition, if we're told the force on a test charge that's placed at a field point, you can find the electric field by saying, hey, what's the electric force it's feeling? How big is the charge? This is like little g equals Fg over m. It can be found using the point charge equation. If we know the size of the planetary charge that's creating the field, that's going to look like this. Electric field equals K big Q over R squared. That's very much like gravitational field equals big G big M over R squared. We find the direction by considering a positive test charge and asking ourselves which way would a positive want to move it? Good. Away from positive towards negative. That's electric field. Electric field. Don't think F for field, think E for electric field. What about electric force? What's our symbol? What's our letter for force? F. We can find it by using Coulomb's law if we know both charges and their separation. That's really similar to Fg equals big G, big M, little m over R squared, or M1, M2 over R squared. We can also find it, well, remember, we also found the force of gravity by going, get the obvious one. Yes? So we can find the electric force by going QE, where little q is the charge that's sitting at that location, and E is the magnitude of the electric force at that field at that location. You can find the force. This is much, much nicer to do than that. In the same way, this was much, much quicker to do than that. Both work. Remember, the direction of electric force is found by saying like charges, unlike charges attract. So for all of these, technically, there are absolute value signs in them. We decide the direction, not with negative or positive, but for forces by saying like charges, unlike charges attract. For electric field, which way would a positive at that location want to move if it could? Oh, I think there's one more. Absolute value sign would go there too, technically. Okay? Since force and fields are vectors, if we have several charges, then we'll need to either add the electric fields vectorially, sometimes tip to tail if they're at angles, or you know what, if they're in a nice straight line, winner minus loser. And for forces, same idea. What's your homework? Try number 1, 2, 3. Skip 4, 5 is good. 6 is good. Number 8 would be kind of like the bonus question that you might have had on your gravity test, except you were trying to figure out where the gravity field was 0. I'm not going to give it. I'm not going to do 7. No, not going to do 9 either. 10 is good. 10 is a job for a free body diagram. Eleven is good. 13 is good. I skipped 12. 15. Skip 16. 17. Okay. So here is the bonus video game. if you achieve certain levels, you can get some bonus marks on your electrostatics test. But let me pause the video recording here.